Good morning or afternoon or evening or whenever you're watching this. Today we are going to talk about related rates problems, which are, I gotta be honest, some of my favorite context-based calculus problems. They're just honestly fun for me to write and fun to do. So we are going to also use the calculator for the first time this year, kind of efficiently. So if you have a calculator nearby, that's going to be helpful. And we are going to, like I said, be working on related rates. And today's lesson is going to be focused on geometry with related rates. And then the next lesson is going to be focused on the algebra of related rates. So what the heck is a related rate? What are we about to do? It's basically implicit differentiation. That's that thing where we had like xy plus 2y squared equals x minus 7. And then we said like find dy dx. And implicit differentiation was the idea that I'm going to take the derivative when x and y are like commingling. And so we took d dx of both sides. And implicit differentiation is just like that, except instead of taking d dx, we're going to take d dt of both sides. So let me show you how it works. So I'm going to jump right into this example. Yes, I know I skipped the big yellow box. The yellow box is there for you to reference later if you forget this video and you don't want to watch it again, but you want a quick refresh. That's going to give you the steps for what's going to actually happen, but I like to do them right in front of you. So Mrs. Vibber is climbing a 25-foot ladder up the side of her house. As I climb the ladder, the top of the ladder starts sliding down. And if I set a ladder up like this, you bet it would slide down. Don't ever put a ladder up against a house like that. That's dumb. But if I climb that ladder and the top of this ladder starts sliding down, my day is not going to go well. And at the moment the top of the ladder is 15 feet from the ground, it's sliding downward at a rate of 6 inches per second. At this moment, how fast is the bottom of the ladder sliding away from the house? Give units of measure. Okay, well, let's do it. So your first instinct might be like, well, if it's sliding down at 6 inches per second, isn't it going out at 6 inches per second? And the answer is no. No, it's not. Because the height and the width of a ladder leaning up against a house is not a linear relationship. It is a Pythagorean relationship, better known as a squared plus b squared equals c squared. So we're going to start with geometry right now and then say, okay, the lengths of the sides of a right triangle have the relationship that a squared plus b squared equals c squared. So there's a and b and c. But I'm not taking a rigid right triangle. I'm going to take this right triangle and I'm going to change the side lengths. And I'm going to change the side lengths over time. So I am going to take d dt, the derivative with respect to t of both sides, because all of these variables can potentially change with time. All right. Now, when we had done implicit differentiation before, when this was an x, I said anytime you take the derivative of a y, you multiply by dy dx. Technically, it's because of the chain rule, but I had said in layman's terms, it's whenever the letter you're differentiating differs from the letter you're differentiating with respect to, you got to leave behind dy dx. Well, the same thing is true about t. So when I go to take the derivative with respect to t of a squared, the derivative of a squared is 2a, but a is not t, so I have to multiply by dA dt. And then the derivative of b squared is 2b, dB dt. And the derivative of c squared is 2c dc dt. And everybody gets a d something dt because none of those letters are t, and I'm differentiating with respect to t. All right, now, what do all of these different derivatives and variables stand for? Well, a is the length of the base. I don't know that right now. dA dt is the rate of change of the length of the base over time. This is dA dt. That's what I wanted. So I'm okay with that being a variable. But I'd really like to know A, so maybe I'll go back and find it in a minute. B is right here. That's the height. Hey, I have that one. dB dt, that's the rate of change of the height. Guess what? I have that too. I am moving down the wall at 6 inches per second, which means that B is decreasing by a half a foot per second, because I'm going to watch my units. That was inches and everything else is in feet. So I'm going to change that to decreasing by a half a foot per second. Equals to C dC dt, and I don't have anything written on side C. Okay, so I got to do some sleuthing right now. So let's go back to A. A is this guy right here. I don't know what it is. C is this guy right here. I do know what it is. I just didn't write it down yet, because it said blah, 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 blah. Mrs. Vibber is sliding down using a 25-foot ladder. Now, I have scribbled all over this, so I am going to simplify my diagram for a moment and say that we knew this distance was 15. We now know that this distance is 25, and by the power vested in me by the Pythagorean theorem, I know 15 squared plus b squared is 25 squared. And if you notice, that is a 3, 4, 5 right triangle. So b here is 3 times 5. This is 5 times 5. So b is 4 times 5. It's a 3, 4, 5 right triangle. And b is 20. You could also just work that through with the Pythagorean theorem. I don't know why I called that b. It's because I erased everything. Just pretend I had said that that was a. Same deal. Because really I had called that a before. My apologies if anybody got spooked. I promise that this still works the same way. So we had a squared plus 15 squared is 25 squared, and a is 20. But I really don't feel like editing this video, so you can cope. All right? So a is 20. And we knew that dA dt is what I'm looking for. And so I'm going to put that there. And then c is the length of the hypotenuse, that's 25. But I didn't find dc dt. So dc dt would be the rate of change of c. Well, c is the ladder. And nothing here said that the ladder was like collapsing. So dc dt is 0, because the rate of change of the length of the ladder is nothing. It's not changing. So 40 dA dt equals equals plus negative 15 equals 0. And so if I add 15 and then divide by 40, dA dt is 15/40, better known as 3/8. Okay, and that's a dA dt. And then it said indicate units of measure. Everything was in feet, so it's 3/8 foot per second is how fast this ladder is sliding away from the wall. So even though it's coming down the wall at a half a foot per second, it's sliding away from the wall at slightly less than a half a foot per second at this given point in the terrifying encounter that I'm having with a ladder. All right? Cool, cool. So now, let's do another one. You want to take pictures of a rocket taking off from a landing pad. You place a ladder on the ground 800 feet away from the launch pad, because, you know, there's fire, on a tilting tripod so that the camera can tilt to follow the rocket's path as it soars into the sky. If the rocket is moving at a speed of 300 feet per second when it is 950 feet higher than the tripod, what should the angular speed of the camera be to follow the path of the rocket? Give units of measure. Okay, so basically, this rocket's taking off. I got a right angle right here, and this tripod needs to tilt to watch the rocket as it blasts into the sky. Now, I'm going to draw a secondary diagram here. So we have this camera over here, okay? And it is 800 feet away from the rocket. And the rocket, let's see, is moving at a speed of 300 feet per second. So this rocket's going up at 300 feet per second. And that's happening when the rocket is 950 feet higher than the tripod. So we're basically ignoring the tripod, that's fine. The rocket's 950 feet higher than the tripod. What should the angular speed of the camera be to follow the rocket. So the camera's got to tilt to look at the rocket as it shoots off into space. Okay. Well, I have an angle in a right triangle this time, so I'm not going to use Pythagorean theorem. I'm going to use right triangle trig. I'm going to use SOHCAHTOA. And if I think about the position of this angle, this is the opposite side. This is the adjacent side. So I am going to use tangent. And let's call this opposite side A and the adjacent B, or maybe just because A is already adjacent, I lied. Let's call the adjacent side A and the opposite side B. So tan theta is going to be B over A. And the angle and these lengths are potentially changing with time. So I am going to take d dt of both sides right here. And say, let's see, the derivative of tan theta is going to be a chain rule. The derivative of the outside, keep the inside, times the derivative of the inside, which would be the theta dt. And over here, b over a is a quotient, so I need the quotient rule. It's the bottom times the derivative of the top with respect to t, minus the top times the derivative of the bottom with respect to t, all over the bottom squared. All right. So now I got to figure out what the heck is going on here. Well, what did I want? I want the angular speed of the camera. So this is the variable I am trying to solve for. So if I am comfortable allowing d theta dt to stay a variable, that means I have to find values for everything else. All right, so starting with theta, I need to find theta when that's 950 and 800. And so if I need to do that, I need to do, let's see, inverse tangent of 950 over 800, right, to find that angle. So I am going to come over here and do arctan 950 over 800. And I believe I am currently in radians, so let me go back to degrees. That is 49.899 degrees. All right, so theta is 49.899 degrees. D theta dt. And let's see, A dB dt. So A, we said, is my adjacent, and that's 800. dB dt is the rate of change of side B, and that rocket is moving up at 300 feet per second, so that side is lengthening at 300 feet per second, minus B, which is 950, dA dt. Well, dA dt is the rate of change of this side length, and it's not changing. That camera is on a tripod. It's just stuck in the ground. So dA dt is 0. And then all over A squared, which is going to be 800 squared. Now, one thing that I just did that I'm regretting is I did this problem in degrees, and I shouldn't have done that because we are in calculus and we are already in radians. So we're all going to pretend that I made up a teachable moment. Really, I just made a mistake. You should only ever be in radians. Okay, I know your brain wants to know, oh, how many degrees is that angle? It's 49 degrees. That's fine, but guess what? You're in calculus, we are always in radians. So I'm going to go back to radians just to re-emphasize that point. So this is 0.8709 radians, and I am going to change that back to radians. Never go back to degrees ever again this year in calculus, radians only. Okay, so then d theta dt is just going to be 800 times 300 divided by 800 squared, and then I need to divide by secant squared 0.8709. So d theta dt is going to be 800 times 300 divided by, let me make this a better fraction for y'all. So 800 times 300 divided by 800 squared. And then I'm dividing that by the secant of 0.8709 squared. And I get 0.155592. 0.155592. And then it says give units of measure. We are in calculus, and we are talking about angles, so our units are going to be radians per second. Now, it never told you what to round to, so this is my chance to say, listen, if you are in calculus and you are specifically in AP calculus, our rule of thumb is this: your final answer needs to be correct to 3 decimal places, rounded or truncated. So you would be allowed to write this as 0.155. You could write this as 0.156 because you rounded the 5 here up because there was a 5 next to it. You could also write this as 0.01 or 0.155592. So you have to either round or truncate to 3 or give more than 3. Okay, any one of those answers would be considered correct. All right, and then we are going to do one more back here before we get to cones are special. So what I would like to do is I'm going to split this video up into 2 videos because I don't like it when they get too long. So I know that there is another page in your notes, and I want you to know that I know that, but you're going to come back soon for the second video. Okay, so you're going to stop here and do whatever I tell you to do, and then come back later to watch this second video. All right, so have a good morning, afternoon, evening, and you will see me again soon.